This video covers Kirchhoff's laws. Now we need to start off with the types of circuits. Again, you don't need to write this part down because you've seen it before and it becomes so easy after you've used it so many times. On the left-hand side, we have a series circuit. You can tell it's a series circuit by the fact that it only has one path as you go from the battery all the way around back to your battery. On the right-hand side, we have a parallel circuit, where if you go from your battery, you reach a certain point, and at this point you can see that we have different paths that we could take to get back to our battery. So we're going to see these different circuits in context with our Kirchhoff's rules. Our first rule is Kirchhoff's loop rule. That tells us that the potential difference in a loop of a circuit is zero. This is one of the biggest ideas in circuits, that the potential difference in a loop of a circuit is zero, meaning that the voltage of all the elements of a circuit must add up to zero. Again, this equation is essentially putting all of that into a formula. And this is because it's based on the conservation of energy. Our potential is providing our change in potential energy, and that change in potential energy has to decrease all the way back to zero in order for us not to gain or lose any energy. So to really imagine Kirchhoff's loop rule, we need to remember that voltage is analogous to height in gravity. So batteries and generators act like charge escalators, lifting charges against the natural tendency to fall and have positive potential. Again, moving downward decreases potential and potential energy. So electrical components use that energy created by the batteries and generators. As the charges fall through the circuit, they lose energy to components such as resistors, which have negative potential. Again, we'll see all of this in circuit form. So remember in our last video, we saw that EMF is going to represent the electromotive force. This is also known as the potential of devices that create a potential difference, such as batteries and generators. Now, for the most part, batteries are going to have a positive potential difference, but there are times when the battery may be labeled as having a negative potential difference. The most important part is going to be down here in color. That a positive potential difference, a positive EMF, is assigned to the strongest battery, and negative potential difference, negative EMF, is assigned to any reversed or weaker batteries, and we'll see examples of both of those situations. In this first example, we're asked to solve for the potential difference across resistor R. So, for these problems, you always want to start with the EMF of the strongest battery and trace the circuit from the positive terminal of the strongest battery to the negative terminal of the strongest battery. Remember that EMF is just another way to say the voltage of our battery. So, 6 volts is going to be our EMF. We'll call this R resistor 1. This is resistor 2, and we'll call this resistor 3. So we're going to start with 6 volts, our EMF, and as we go across resistor 1, we're going to lose some of that voltage due to resistor 1. It's going to use up some of that potential. After we pass resistor 1, we're going to go across resistor 2, and again, lose some more voltage. And then finally, we're going to go across resistor 3, and we have to lose the remainder of that voltage because, again, Kirchhoff's loop rule says that all the potential we have at the beginning plus all the potential that we lose across our circuit has to be equal to 0. So we have 6 as our starting EMF minus the voltage of the resistor, what we're trying to solve for. The second voltage that we lost was 3 volts, and the third voltage that we lost was 1 volt. So you should get 2 minus VR1 equals 0, or just VR1, the voltage loss across resistor 1, equal to 2 volts. In the second example, we have 2 batteries, but always start with the strongest one. Here, we can see that this 12 volts is greater than 4 volts, so we're going to start with the 12 volt. Again, we start with our EMF of our strongest battery. We're going to move from the positive terminal across. We're going to lose some voltage because of that first resistor. And then now you want to look at how the second battery is oriented. Remember that if this is a negative and this is a positive, if we go across from here to here, we are increasing our potential. If you go from the negative plate to a positive plate, we're going to have a positive change in potential difference. So that means we're actually going to be adding the potential across our second battery. I'll put B for battery 2. And then as we past it and go across our last resistor, we'll call this resistor 2, again, we are going to lose some potential. Again, no matter what, the potential that we have at the beginning plus all the potential across our circuit has to be equal to 0. So if we plug in all of our numbers, I get 12 minus VR1 plus 4 minus 2, which gives you 14 VR1, or our voltage across our first resistor, equal to 14 volts. Same situation, we're still trying to solve for our potential across our resistor. You're going to start with the positive terminal, go around, again our EMF minus our voltage dropped across the first resistor. Now here you want to notice the orientation of that battery. We're going from a positive plate to a negative plate. That means we're going to have a decrease in potential. So that means we are going to be subtracting that 4 volts. So we are subtracting the voltage of our battery. Call this battery 2. And then we're going to continue on and drop more voltage for our second resistor. Again, always equal to 0. When you put in all of your numbers, again 12 for your strongest battery, minus the voltage drop across the first resistor, minus the voltage drop of the battery, minus the voltage drop across the second resistor, you get the voltage drop across the first resistor to be 6. Now in this situation, we actually have 2 different ways that our current can go. So we have to write 2 different equations. One that goes one way, and another that goes the second route. Each of these has to lose 12 volts in total. So all we're concerned about is the loop that contains the R resistor. So we have our EMF to begin with. We're going to follow the red path all the way around, and we're only going to drop voltage due to that resistor. Again, it's going to be equal to 0. So that means the voltage drop that we lose across that resistor is simply 12. So let's look at Kirchhoff's junction rule. This tells us that the current entering a circuit junction must equal the current leaving the junction. Current in must equal the current out. Again, this is based on the conservation of charge. Since charges cannot be created or destroyed, the number of charges entering and leaving must be equal. Charges cannot appear or disappear. Remember that the direction of positive current is from the positive terminal of a battery to the negative terminal of a battery. Again, we know that electrons are actually the ones that move, but it's easier for us to think of protons moving. So this first example, we're going to start from our battery, and we see that we have 8 amps. Again, this is our current. Make sure you look at units here. This is the current that comes out of our battery. Now, in this particular circuit, we don't have any breaks in our circuit. We have no other path but one. That means the current across my resistor is equal to just 8 amps, the current coming out of my battery. In this example, we have 2 batteries. So for now, we're just going to take it that our positive plate is going to send a current out in this direction, and we know that that is 6 amps. This other battery is going to send out a current going this way, and that is 2 amps. So here, when they meet at a junction, these 2 currents are going to go through this middle resistor, and then as it exits this second junction, 6 amps is going to continue out this way, and 2 amps are going to continue out this way. So the current in must equal the current out. So our current going through our resistor is going to be 8 amps. Now this one's a little easier. Again, we start from our positive plate. We have 9 amps coming out. At this junction, some of our current goes this way, and we know that is 3 amps. That means the other part of the current must be 6 amps. So that when they join up together back here at this other junction, we have 9 amps that return back to my battery. So the current across our resistor is 6 amps. Another easy example, we have 9 amps coming out of our battery, again from our positive plate. 9 amps cross our first resistor. We come up to a junction. 3 amps go this way, meaning 6 amps still go the other way. It didn't matter that we now had this resistor here. Again, at this junction, we meet the 3 and that 6 amps back up, and we have 9 amps returned to our battery. So, again, the current across the resistor is still 6 amps. So this is a summary of what happens with voltage and current for both a series and a parallel circuit. Remember that for voltage, in a loop containing a power source is 0. Again, that's one of the most important pieces coming out of Kirchhoff's rules. This has to do with the conservation of energy. For current, the current entering a junction must equal the current leaving a junction. Again, going back to the conservation of charge. So if there is no junction, then the current is the same everywhere. If the current reaches a junction, it splits up, but must still total to the amount that entered the junction. Now let's try putting it all together. Here we have a circuit with 3 resistors in series. Here it's going to be very important for you to pay attention to units. This is 6 volts, which tells you that this is the EMF of my battery. This is 8 amps, which tells you my initial current. Again, my current goes from the positive terminal all the way around. Because all of these resistors are in series, we know that the current, the amount of electrons coming out of my battery, has to cross this resistor. So this also has 8 amps. We continue to move across a resistor. Still no junctions, that means my current is still the same. We continue to move through our circuit. Again, no junctions, we should still have the same 8 amps all the way across. Now, we need to go back and look at our voltage. We know that we start with our EMF, our battery, and as we go across the first resistor, we're going to lose some of that voltage. As we go across the second resistor, we'll also lose voltage. And as we go across a third resistor, we also lose some more voltage. And again, all of that together will always equal to 0. So putting in our numbers, we have 6 minus VR1 minus 3 minus 1. Here we had enough information to find out that our voltage drop across our first resistor is 2 volts. And our last example. Here we're asked to solve for the missing voltages and current, and this one's a little trickier. So you want to start with our loop rule, meaning that we're going to start with our 9 volts, which is our EMF of our battery, and we're going to create our loops. Well, first off, we're going to go through one loop here. We'll label this as loop 1. And the other option we have is to go through loop 2. So both of those loops are going to have their own functions. So for the first loop, we have the EMF minus the voltage drop across the first resistor. That has to equal 0. For the second one, we have our EMF minus the voltage drop across the second resistor, and again, that has to equal 0. So that means that the voltage drop across the first resistor is equal to 9 volts, and the voltage drop across our second resistor is also equal to 9 volts. So we know that this is 9, and this is also 9. Now we can apply our junction rule. This means that our current in has to equal our current out. So we can look at the current going in, which is 3 amps. So we have 3 amps coming out of our battery. It's going to reach this junction. Some of the amps are going to go this way, and some of the amps are going to go this way. So we have 2 different currents here. But together, they need to add up to those 3 amps. So we're going to label our initial current as I naught. As we go through our first resistor, that current has to add up to our current of the third one. Now here we actually have enough information to figure out our current of the second one, which is simply 3 minus 1 equals 2. Yay, simple math. The reason that we're emphasizing these very simple circuits is that they are going to get harder, but these are the foundations of understanding how to do these types of problems. So even though it might look simple, make sure that you understand why and what we're doing so that you can be able to apply it to more complicated circuits.